Hello, this is Module 4, where we are going to talk about voltage and current laws. And simply put, these are the fundamental laws that are useful for solving for currents through the elements in a circuit, as well as the voltages across elements in a circuit. So to begin, let's first just kind of overview some simple circuit models. Now, we've seen these in some of the past lecture modules, but it's worth going over because we'll see them over and over again at this point. First, a short circuit is defined as that which connects two nodes A and B together via a wire or a perfect conductor with resistance 0. So if that's the case, then the voltage between A and B must be 0 volts. Okay. You can think of it as the voltage potential at A equals B, or the difference between A and B is 0. So that's defined as a short circuit. An open circuit is defined as a break between points A and B such that there cannot be current flowing through this element. So the other way to think about it is an element at which the resistance is infinite, as defined as an open circuit. A switch is defined as an element that can toggle between being short and open. So, and you'll see this little symbol like this, and little arrows directing at which point this rotates. And another useful circuit model is an ideal battery. So I might draw it like this to indicate a battery. This is not really a circuit drawing, but before we get to the model drawing, I can just draw it like a physical battery between A and B. And in this case, I'm just defining that as, for example, having some potential across that. In this case, being 1.5 volts. It can be anything. But to model that in a circuit schematic, we often model that as an ideal voltage source. So in this case, defined as Vs as being the 1.5 volts, but also with having a series resistance following the voltage source. So when this is not connected, in other words, it's open circuited, so we don't have a closed loop, we have 1.5 volts across this entire element between A and B. And that's because when this is open, there is no current going through resistor Rs. Therefore, there's no voltage drop across Rs. Therefore, the voltage difference between A and B is still 1.5 volts. So note that the series resistance Rs must be greater than 0. Otherwise, if we short-circuited this battery, in other words, connected A directly to B, we would have infinite current. But we know that that can't happen, so we know that there is some physical resistance there that is part of the battery that limits how much current can be drawn from the battery. So if we do just that, we connect node A of the battery to node B of the battery, in other words, short circuit it, we will find that there can be current flowing through the circuit, defined as Is. So this is what we call the short circuit current. Anytime we do this, we would use this terminology. And like I said, I will not go to infinity because this is not an ideal conductor with 0 resistance. There is some internal resistance to the battery. And that can be found just simply with Ohm's law, where Is is going to be the battery voltage divided by the series resistance, the source resistance. And note that we might have a different symbol. Sometimes instead of an ideal voltage source, you'll see this symbol here where it's 4 lines kind of toggling in size. This is indicative of a battery. It's a voltage source, a DC source symbol specifically for a battery. So I think the best way to understand the voltage and current laws is by example. So we're going to use the basic example of modeling a flashlight. We know that a flashlight consists of a few batteries and a light. So specifically, I'm going to model it as having 2 batteries. We put them in series such that, for example, if each battery is 1.5 volts, if we put them in series with one another, we have 3 volts across the entire battery set. Note we can find that as by starting at the lowest potential, adding 1.5 volts, adding 1.5 volts to get the total of 3 volts. We also know that the flashlight can usually be turned on and off, so we can model that with a switch. In other words, it can be open or short circuit. Open meaning no current will flow. Closed meaning now we have a closed circuit and current can flow through the system. We'll model the lamp as just being a resistor. And we'll also note that there's wiring in there, and the wiring may not be ideal, so there could be some resistance in the wire. So if we go from this physical model on the left to a circuit schematic model, we can go ahead and write that as a 3-volt source, and we know that that battery will have some kind of source resistance, as mentioned in the previous couple slides. The resistance of the lamp is being defined as RL. And then if we're modeling the wiring resistance, we can model that as resistance RW. So to solve this circuit, we're going to use something called Kirchhoff's laws. And there's actually a typo right here. Kirchhoff's is going to have 2 H's in it. Okay, so there are about 5 basic steps to solving any circuit, specifically solving for the currents and the voltages in the circuit. This works with any type of element, so you really kind of keep this in your back pocket. You might want to print out these steps until you really become comfortable with them. Okay, so the first step is to redraw the simplified circuit if possible. I've redrawn it right here. It's just we can't really simplify it any further, at least now. We haven't learned how to combine elements yet. Step 2, identify and label all nodes in a circuit. So we talked about nodes the other day in class, but a node, as a reminder, is any point within a circuit where 2 or more elements meet. So this circuit has 4 nodes drawn here in red and labeled as A, B, C, and D. Where A is kind of the point, it's really this whole section here, the wire and the pointer are the same thing, that joins the element 3-volt voltage source element with the resistance RS. B likewise joins element RS to element RL, and so forth. Step 3, define unknown currents in each branch, whereas a branch is defined as a segment of elements with a node at each end. So there's a branch between A and B, one single branch, for example, that consists of element RS. There is a branch between A and D that consists of a single voltage source. Okay, so this circuit has four branches. This, let's see. Sorry, I had a little bit of a technical problem here. Reiterating, this circuit has 4 branches. So the objective is in each branch, we're going to define a current, and note that we can do so with an arbitrary direction. So I'm going to write that there's a current IS going from left to right through the RS element. There's IL going down through RL, IW going right through RW, and IP going between D and A through the 3-volt voltage source. Direction is completely arbitrary, as we're going to find out later. We'll really solve for the magnitudes and the directions at a later point. Okay, so step 4 is for each element, we're going to define the unknown voltages across those elements. So this circuit has 4 elements, and 3 of them have unknown voltages. So element RS, we're going to define that voltage as Vs, and so we define the polarity of Vs based on the direction that we assumed in step 3. So since we assumed that Is is going from left to right, based on passive sign convention, that current should be going into the positive terminal and out of the negative terminal. Therefore, we have to define the polarity of Vs as being positive on the left and negative on the right. Likewise, for the other resistors, so for resistor RL, for example, since I've drawn the current going down, I must assume that the positive polarity of voltage VL is on the top and the negative on the bottom, and then so forth for RW. Step 5, we're going to use Ohm's law, or whatever I should really say here, or, whoops, let's see here, erase, or the elements VI relationship. So we're going to use the IV relationship for the element if they're resistors in this case, since in this case we're going to use Ohm's law. But we use that relationship to express the unknown voltages in terms of those defined branch currents. So we know that our unknowns in terms of currents are shown here on the left. So for Ohm's law, since we use passive sign convention, this is very straightforward. It's just Vs equals IS/RS. This is why I tend to use a convention where if I've defined RS, I'll try to define the I and the V with the same subscript just to make it really easy to read. And so there's my 3 Ohm's law expressions for my unknown voltages. And then finally, we use Kirchhoff's laws, again a typo, Kirchhoff's laws for solving for all of these unknowns. Okay, so we know that charge must be conserved in a closed system, i.e. a circuit. So this manifests as 2 laws. One of the laws is going to be in terms of current, and one of the laws is going to be in terms of the voltage. So first, Kirchhoff's current law, or KCL, is defined as the algebraic sum of currents entering a node must be equal to the sum of currents exiting a node. In other words, the sum of all currents at a node must be equal to 0. Hence the manifestation of charge conservation. So for example, if we have a node, and we're assuming this is part of a closed circuit, so there will be current, and I've defined arbitrarily I1, I2, I3, and I4. Since I've got I1 going in, I2 going in, I3, and I4 going out, I can write this as the sum of I1 and I2 must equal the sum of I3 and I4. I could rewrite this by defining arbitrarily that going in is a positive, so I could write this as I1 plus I2, and exiting is a negative, minus I3 minus I4, or I could define this as going in as negative and coming out as positive. In any of these 3 cases, they're all equivalent definitions. So it really doesn't matter. You just should get used to coming up with a convention and sticking to it. Sticking to it is important because that will help you debug your problems and help for readability later.